Okay, welcome everyone, and thanks for joining this session of the virtual seminars in economic theory. Today we have Nima Haghpanah from Penn State presenting the paper Selling to a Group. This is a joint work with Aditya, Kuvalekar, and Elliot Lipnowski. Today with us we have guest panelists as well, Smolin and Mallesh. The format of the seminars is as usual. We have a 60-minute presentation with time for interim questions from the panelists. This is followed by a 15-minute Q&A sessions with panelists and the audience. We request all attendees to keep your microphones muted during the talk. However, please post comments and questions in the chat. Co-authors will have a look and might interrupt Nima if something is pertinent. But also you can unmute yourself and ask questions directly. The talk is recorded. Before I hand over to Nima, let me invite you to our next seminar next week. We have Muhammad Akbarpur from Stanford discussing investment incentives in near optimal mechanisms. Thank you, Nima, and the mic is yours.
All right, thank you so much, Max. Thanks for all the organizers for inviting me. I'm very excited to be here. Thanks to Mallesh and Alex for joining as panelists. My co-authors, Aditya and Elliot, are both here as well. So if you have questions, you can type them in the chat box. They'll be answering those. But also, yes, as Max said, feel completely free to interrupt both panelists and the rest of the audience with questions. I don't have too much stuff prepared, so I'm happy to take it slow and discuss as we go. So this is a paper in which we study a setting with a seller who has a product to sell to a group of buyers who pay for this product using some amount of money that they collectively own as a group. So there are two important features of this model that I want to highlight at the get-go. One is that this product is not sold to any individual, but instead it is public to the group. So everybody in the group gets to enjoy it if it is sold. And second, and similarly, the money doesn't come from any individual's pocket, but instead comes from this pool of money that this group collectively owns. Let me give you two examples just to be a bit more concrete. Imagine selling a product like a software product to a company. This company pays for this product using the company money that they collectively own, and this software is used by all the members of the company, not just the CEO or the CTO. Another example is selling construction services to a city council who pays for this construction service using the city's budget. So it's, again, a collective pool of money that is paying for this product. Now, in our setting, these agents in this group are going to have different opinions about how much is this product worth in terms of the group money that they have. So, for example, they may have different opinions about the value of this product because they think they have different opinions about the opportunity cost of spending this group money on other products and projects other than paying it for this product. So then the question is, given that this heterogeneity of preferences exists among these agents, what kind of mechanisms should the seller design to maximize the expected profit? So what are the seller's optimal profit maximizing mechanisms? So I'm going to just jump ahead into the model to make everything more clear, and then we can discuss some more. So there is a set of n agents. These are the agents in the buyer group, so agents 1 to n. And there's a set of outcomes. An outcome is simply a pair. X specifies the probability that this good is sold to the group, and M specifies how much the group pays. So there's a space of all possible outcomes is specified by the space of all possible X and M. And as I said, each agent in this group has a preference over all possible outcomes. These preferences are going to be specified by a payoff function for each agent I. So agent I's payoff is VI times the probability of allocation minus how much the group pays. This VI, you can think of it as the value of agent I. It is independently drawn from all other values from a known distribution Fi that is assumed to be regular in the Myersonian sense. So let me offer some interpretation of how we should think about this VI. VI is how much agent I thinks this product is worth in terms of the collective money that this group has. For example, if this agent is asked to compare an outcome in which the group gets the product and pays VI for it, then this agent's payoff will be 0. So then this agent is indifferent between the outcome in which the group pays VI for the product and an outcome in which the product is not sold and the group doesn't pay anything. So this VI represents how much agent I thinks the product is worth in terms of the group money. So we are not explicitly modeling the outside option of what this agent thinks could be done with this money if not spent on this product. This VI just captures that. The payoff of the seller is simply the profit of the seller. So it's just how much money the seller receives minus the cost of producing this product if this product is produced. And what we would like to do is to study all mechanisms and identify which ones are profit maximizing. So the space of all mechanisms by the revelation principle is the pair X and M that map the reported values of the agents to the set of possible outcomes. So specify whether or not the product is sold and how much the group pays. You want mechanisms to be interim individually rational and Bayesian incentive compatible. Interim individual rationality states that the expected utility of agent I, if she has value VI for the product, then the expectation is taken over the values of all other agents. This expected payoff must be non-negative. Bayesian incentive compatibility is standard. It just says that if agent I with value VI reports her type truthfully, that maximizes her expected utility, taking an expectation over the values of all other agents over all possible reports that this agent may be able to report. But I wrote the individual rationality explicitly here because as innocent as it looks like, it is a very strong assumption. What it is saying is that every agent must get non-negative utility from this mechanism. It is essentially saying that each agent in this group has the power to veto the mechanism if the expected utility of that agent is negative. So if even a single agent vetoes this mechanism, then no agent in this group will be able to participate and engage in this mechanism. So this is a very strong veto power that all members of this group have. I'm going to come back later to think about other possible ways to think about how do the agents decide to participate in this mechanism. For now, we're just saying that every agent, knowing their own type, must be willing to participate in this mechanism. Otherwise, the mechanism is vetoed, nothing happens. So this is the setup, and the question, as I said, is what are the seller's profit maximizing mechanisms? And to develop some intuition, I'm going to start with an example with two agents and certain distributions, uniform distributions, and then we're going to extend that to our main result, which is a characterization of optimal mechanisms. So suppose that there are two agents, and suppose that the production cost is 0 for simplicity. These two agents have uniform distributions, but not identical distributions. So agent 1's distribution is uniform from 0 to 2. Agent 2's distribution is uniform from 0 to 3. We would like to know what is the revenue maximizing mechanism because the cost of production is 0. You will notice that a special case of our setting when n, the number of agents, is equal to 1, is just a standard problem of selling a good to an agent, where we know from Meyerson and all the other papers that the optimal mechanism would be to simply put a price tag on the product and ask this agent to either agree or reject this purchase at that price. In this example, if there is only one agent with this distribution, the optimal price to offer this agent would be 3/2. So then it would be natural to try to think, well, how can we extend this posted pricing mechanism to the case of two agents? One immediate way, which is perhaps a bit naive, is to say, well, let me just put a price tag on this product and ask one of these agents if they think this product should be sold at that price. For example, here, maybe because the CTO tends to have higher values than the CEO, maybe I can just ask the CTO if he thinks the product should be sold at that price. So then I can sell the product at price 3/2 if the CTO agrees. This mechanism is not individually rational because the CEO is never asked what she thinks. And it could be that she thinks that the product is worth nothing. So if her value is 0, she thinks that the product is worthless. But then the mechanism sells the product with a positive probability, which is 1/2, and then the group pays a positive amount, which is 3/2. So her expected utility would be negative, so she'd want to veto this mechanism. So then how can we adjust the definition of a posted pricing mechanism to take care of individual rationality? Instead of asking only a single agent to approve the price, maybe we can ask everybody to accept or reject an offer to sell the product at price P. Then by definition, this mechanism is going to be individually rational. If each agent thinks that the value is less than P, they're going to not agree to the sale and the product is not going to be sold. We can optimize over P by solving this problem, which is the expected profit, the price, times the probability of sale. The numbers don't matter too much. What matters is that this posted pricing mechanism is not optimal. The optimal mechanism has a much more nuanced allocation rule. In this example, this is that allocation rule. It says the product is sold if and only if a weighted sum of the two agents' values is above a given threshold. For weights and threshold that is specified down here, again, the numbers don't matter so much. What matters is that this allocation rule is based on some weighted optimization of the agent's values. And this is exactly what our main result is going to say, that specifies the optimal allocation rule as a solution to a weighted optimization of the agent's virtual values. And then we're going to go on from there. So this theorem characterizes optimal mechanisms. It consists of 3 statements. Statement number 1 specifies what the optimal allocation is. As I said, it says that the allocation is a maximizer of a weighted sum of agents' virtual values. So in the example before, it was of agents' values, but in general, it has to be a weighted sum of agents' virtual values. Statement number 2 specifies what these weights are. It says that these weights must themselves be a solution to another optimization problem of minimizing weighted virtual surplus. So statement 2 characterizes what these weights are. And statement 3 specifies what the transfer rule is to go with the allocation rule in order to make the mechanism Bayesian incentive compatible and interim individual rational. So let me just fill in the gaps here. Allocation is for the product to be allocated if and only if a weighted sum over all agents of each agent has a weight W star I. You multiply that by the virtual value of agent I, and you sum over all agents. If this weighted sum is more than the cost, the product is going to be allocated, otherwise not. For the virtual value is just the standard Myersonian virtual value. So this specifies the allocation for a given profile of weights W star for each agent I. The question is, what are these W stars? That's what part 2 says. Part 2 says these weights W star must be a solution to this minimization problem of minimizing over all weights that are distributions over agents. So these WIs are non-negative for each agent I, and they sum up to 1. Then you think about the expectation of a weighted sum of agents' virtual values minus C and 0. And the weights that minimize this problem, those are the appropriate weights. Finally, part 3 tells us that there is a transfer rule that goes with the specified allocation rule that makes the mechanism Bayesian incentive compatible and individually rational. The short version of it is that the payment identity must be satisfied so that the Bayesian incentive compatibility holds. But the payment rule itself it's a bit complicated and it's nuanced, so I'll come back to it later.
Is it, sorry, is it obvious that you can satisfy multiple IR constraints simultaneously when you're using this weighted rule and a single transfer rule? Or are you going to say more about that?
It is clear that you could satisfy it because you could just pay the group $1 million. So then all these IRs are going to be satisfied. So I don't think satisfying them is that hard. I mean, it is possible to satisfy them.
I see. Okay.
So right, whatever transfer rule that you have that makes it Bayesian incentive compatible, if you make an unconditional transfer large enough to the group, that will also satisfy IR. But in fact, what is the best way to do so? That's actually an excellent question, and we're going to come back to that.
Yes, Nima, maybe related, maybe not. What kind of implementation of this mechanism do you have in mind? In your example, for example, do you expect that software company approach individually CTO and CEO and get the bids or some sort, or you think about some other mechanism?
No, I mean, that's a great question. And we are allowing for this seller to interact arbitrarily with these individuals. So that's in a general way, that's the way we are thinking about it. But I guess what this result is telling us, and then we're gonna learn a little bit more when we talk about these weights W star, is if the seller wants to interact individually with each members of this group, how much weight should they put on different agents' opinions? And that's something that we're going to learn once we think about what these optimal weights are. But yes, for now, we're giving full flexibility for the seller to interact arbitrarily with each individual member in this group.
Okay.
All right. So I think this is going to come back and address Mallesh's question a little bit. I'm going to start by proving this theorem in 2 steps, and then we're going to think about what the meaning of this mechanism is and what are these weights. So the proof sketch is going to be just 2 steps. There's going to be an implementation step, and there's going to be a duality step that I'm going to go through one by one. So what is the implementation step? I would like to first understand, for a given allocation rule X, when does there exist a transfer rule that makes my mechanism Bayesian incentive compatible? This would be in parallel to what we do in the standard setting, and later I'm going to compare to that, where individual transfers are allowed. We first think, well, what are the implementable allocations? And then among all these possible M's that could implement a given allocation rule, what is the optimal remedy that makes this mechanism not only incentive compatible, but individually rational? And I'm going to show you the answers, and then we're going to compare the answers to what we could get if we have a setting in which individual transfers between the seller and the agents are allowed. So an allocation rule X is implementable with some transfer rule M, if and only if the interim allocation rule X, according to that allocation rule, is monotone, non-decreasing for each agent I. So it just says, think about Xi, capital Xi of Vi, which is specifies a probability of allocation if agent i's value is vi. This must be non-decreasing in vi for all agents I. And then it says, among all these transfer rules that could implement such an allocation rule, the optimal revenue in a way that it is also interim individually rational would be to take the minimum over all agents, their expected virtual surplus according to that agent, which you can obtain by multiplying the allocation rule by the virtual value of that agent. So given these two steps, what we can do is to basically formulate the problem in terms of an optimization problem over X and just ignore M, because now we can just represent revenue or revenue in terms of just allocation. Now I'm going to compare these two statements to what we have in a setting where we still have a public allocation, but we could have individual transfers between the agents and the mechanism. In that setting, the implementation part remains the same, that an allocation rule can be implemented with some transfer rule. Here, this could be individual transfers, if and only if we have an interim monotone allocation rule. And among these mechanisms, the optimal revenue is the sum over all agents, their virtual surplus. So you'll notice that the difference is mean versus the sum, but this statement is the same. But I'm going to argue that the reason that we have a mean versus the sum here is, in fact, that the arguments that are behind these two similar looking statements are completely different when we talk about individual transfers versus public transfers as in our setting. So let's think about the individual transfer setting. How do we prove these standard arguments? What we say is that, well, if I have an interim monotone allocation rule, I can let the interim transfer of each agent satisfy the payment identity. So this would be the expected transfer of agent I, as long as it satisfies the payment identity, where this U lower bar is the transfer that the lowest type of this agent makes. Then I have a Bayesian incentive compatible mechanism. The problem is, in our setting, we cannot just allow each agent I pay MI of VI because we have a public transfer. We cannot have individual transfers between the seller and the buyers. So the question is, if I give you a profile of interim transfer rules that satisfy the payment identity, when can I implement it with a public transfer rule? And that's exactly what's going to be different in our setting compared to the standard setting with an individual transfer. So the question is, when would there exist a public transfer rule that induces a given profile of interim transfer rules? And the answer is that this is possible if and only if the expected transfers according to these given profile of interim allocation rules for all agents I and J agree with each other. So this is just the law of iterated expectations. It says if I have a public transfer rule, if I calculate this expectation according to the interim rule of agent I, this obviously must be the same as if I calculate this expected transfer according to the interim transfer rule of agent J. So it is clear that this is a necessary condition for implementation of a given profile of interim allocation rule. What should be surprising and was really surprising to us was that this is really the only constraint that existence of a public transfer rule imposes on the interim transfer rules that you could implement. And the proof is quite simple. I can just show you what, if you give me a profile of interim transfer rules that satisfy this property, I can show you what a public transfer rule satisfies, induces these interim transfer rules. And here is that. You could just say, let's let the group pay the multiplication of all the agents' interim transfers. We just normalize it appropriately. First of all, by definition, this is a public transfer. This is how much the group pays. So then the question is, how do we see that this public transfer is in fact inducing the given profile of interim transfer rules? So then you just have to say for each agent I with value VI, what would happen if I take the expectation of this ratio over V minus I? Well, you can take VI out because VI is fixed. So MI VI times the expectation of this multiplication divided by this constant. And this constant is exactly such that the expectation over all V minus I canceled with this denominator. So you're left with MI of VI. So the only constraint that the existence of a public transfer imposes on interim transfer rules is that they agree in expectation. So now that we have this constraint, notice that once I choose a U bar I for any agent, so I specify how much the lowest type of each agent I gets. This pins down the transfer of agent I, which basically then says that it must pin down all the transfers of all other agents because it pins down the U bar J for all other agents J. So instead of having n degrees of freedom, as we have in the setting with individual transfer, we only have 1 degree of freedom here, which is that once you figure out U bar I for one agent, all the other U bar J's are going to be pinned down as well. So then what do? You choose this degree of freedom such that one agent's IR binds and every other agent's IR is satisfied. And it turns out that exactly the agent whose IR constraint binds is exactly the agent who minimizes the expected virtual surplus. So then the revenue that you make from this mechanism is the minimum over all agents, the expected virtual surplus according to that agent. So to summarize this rather long discussion, what we said is that the optimal to optimize revenue, you should choose an X that is interim monotone, and then your revenue will be this. So summary of this discussion is this: you maximize overall allocation rules that are interim monotone, and then you get a profit of or revenue, assuming cost is 0, of this much. So now let's relax monotonicity. Let's think about all allocation rules, and then just verify that the solution that we're going to develop does in fact satisfy monotonicity eventually. And this is going to be our second step, which is duality. So let's think about this max-min problem as a 2-player zero-sum game where the row player is the maximizer who chooses the allocation, and the column player is a minimizer who chooses an agent. And then the payoff that the maximizer gets is the expected virtual surplus according to agent I and the chosen allocation rule by the maximizer. Let's allow the minimizer to randomize over all agents. That's not going to change anything. So we could just say, let's let the minimizer to choose a distribution over agents according to probabilities Wi for each agent I. And then the payoff will be the expected payoff with the probabilities Wi for each agent I. Now we can apply the min-max theorem. We could say, we could flip the order of max and the min. We can let the minimizer choose first a distribution over agents, and then the maximizer choose an allocation rule X, and then the payoff to the maximizer would be the expected virtual surplus according to the randomization over W's and the randomization over which agent is chosen. The nice thing about flipping the min and the max is that we know how to solve this inner optimization problem. This inner optimization problem, as I have said already, is to just allocate the product whenever the weighted sum of all agents' virtual values is positive, and not allocate the product whenever this weighted sum is negative. So then we can get rid of the inner max and replace it with this expression that says the product is allocated whenever this weighted sum is positive. So then our theorem is established. We know what the allocation rule is, and we know that the weights must minimize this expected virtual surplus. I'll stop here if there's questions.
And I guess I have a question. What can you say about irregular case? So where in this construction use regularity of distributions? And can you say something about irregular case? What how ironing would look like in this setting?
Excellent question. So in fact, everything I said, you could basically, if you have the iron virtual values here, as long as the solution to this eventual problem, when you maximize the weighted sum of iron virtual values, that results in a mechanism that is in fact interim monotone, then you're all good. And that's exactly what happens. So everything I said could be extended to the case where you have irregular distributions, then you just do the ironing for each individual and then replace their virtual value with the iron virtual value.
Okay, so you just make it for convenience. It's not essential for the result.
No.
Sorry, can I just to fully understand, the only source of asymmetry here is the distribution asymmetry, right?
Yes.
So if the distribution of these were to be the same,
yes,
then all weights would be the same?
Absolutely, yes. Then the all weights would be the same. You just look at the average virtual surplus and you allocate if and only if that's positive.
I see. All right, thanks.
But then continuing on this, the question is now, how would asymmetry affect the weights that you choose? Meaning, which agent would you choose a higher weight for? Which agents would you choose a lower weight for? And we already have developed, hopefully, some intuition about that, which is that in the Nash equilibrium of our game, where the minimizer chooses an agent, the minimizer chooses an agent that minimizes. If there is a positive probability of choosing an agent, that must mean that that agent is minimizing the virtual surplus. Otherwise, you would not put a positive weight on it. And the agent who minimizes the virtual surplus is an agent whose IR constraint binds. So in other words, these weights are going to somehow represent the dual variables corresponding to the IR constraints of the agents and are going to be higher for the agents whose IR constraints, in a sense, bind more severely than the others. So it's somehow going to represent the binding IR constraints. And that's where I'm going to go next. So the question is, which agents are going to have a higher weight in this mechanism? And the answer to that is that the weaker agents, so agents who a priori have lower values, are going to be assigned a higher weight because their IR constraint binds more heavily than the agents with higher values. And this means that in terms of the interpretation of this mechanism, as Alex was asking before, the seller should, when they're interacting with different agents within this group, you should assign a higher weight to the opinion of agents who tend to have ex ante lower values than the ones who have a priori higher values. So the proposition that we formally have, this is a special case of what we have in the paper. I'll just show you this special case, is that if the virtual value of agent 1 is smaller than the virtual value of agent 2 in the hazard weight order, then agent 1 has a higher optimal weight than agent 2 does. So I'm just going to interpret this as agent 1 is weaker than agent 2 in the sense that a priori they have a lower value. I will show you another formulation that is more directly in terms of values instead of virtual values momentarily. But for now, I'll just point out that this hazard rate order, notice that it's a stochastic order. It's an order on these random variables. These are random variables. These are virtual values that are random variables. So it's think about the distribution of the agent I's virtual values. And it's saying that if the hazard rate for agent 1's distribution is lower than the hazard rate for agent 2's, then agent 1 has a higher weight. At a very high level, I'll just interpret this as agent 1 has a priori lower values than agent 2. To just get the insight, the intuition again, I'm going to go back to the case of two agents, where one agent has uniform distribution from 0 to 2, the other one has uniform distribution from 1 to 3. So agent 1 has lower values. Agent 1 is the weaker agent. And I'm going to argue that, I would like to argue that the weight assigned to agent 1 should be higher. I'm not going to do that. I'm going to argue that if you're going to only listen to one agent, it should be agent 1 and not agent 2. So if you just want to choose one agent and just have the allocation depending on the value of that agent, it should be agent 1. Why? Let's suppose that you want to only listen to agent 2. Well, remember, what we could do is to post a price, optimal price for agent 2, and sell if and only if this person agrees. The problem was that this mechanism is not individually rational. So you have to make it.
You've changed the distribution for the CTO. It used to be 0, 3.
In this example, it is 1, 3, yes. In the original, it was 0, 3, yes.
Then the optimal price would be 2. So
sorry. No. No, the optimal price is still 3 over 2. If you
Oh yeah, you're right. Sorry.
From the row.
No, sorry.
I almost thought for a second that was all right, good. Excellent. So the price is 3 over 2, which means that this mechanism is not IR because when agent 2's value is 0, she thinks she's expected payoff, her payoff is going to be negative. So you have to make a transfer to the company to make the IR satisfied. But this transfer is so large that essentially you make 0 profit if you want to only listen to the CTO. What if you only listen to the CEO? Then you could say the price is 1 if the CEO agrees. Then you don't have to pay any transfers because the CTO's IR is always satisfied. He always thinks the product is worth at least $1. So you don't have to make any transfers. You could make positive revenue by listening only to the CEO. So this is, I hope at least this gives a high level intuition as to why weaker agents are more important if you want to choose one agent to listen to. As I said, I have a more direct statement in terms of the values themselves instead of the virtual values. Here's that statement. It's not a direct corollary, but it's one of the statements we show in the paper. Is that if V1 and alpha V2 are identically distributed for some alpha less than 1, then alpha V star 1 is more than V star 2. So what this is saying is that if the distribution of agent 1's value is lower than agent 2's in a way that if you multiply agent 2's values by a number less than 1, they become identical, then not only V star 1 is higher than V star 2, V star 1 is much higher than V star 2, meaning alpha, which is a number less than 1, multiplied by V star 1 is still higher than V star 2. So let me just give you a sketch of the actual proof, the way we do this. So this is the statement. Here's the sketch of the proof. You say, suppose for contradiction that W1 less than W2 are optimal weights. Here's the key step. It says you have a weight W1 that is less than W2 and 2 random variables, one of which is stochastically higher than the other one. So V2 is higher than V1. Which random variable is higher? Would it be higher if I multiply the small weight by the small random variable and the large weight by the large random variable, or large weight by small random variable, small weight by large random variable? If you want to minimize, you would want to multiply the large weight by the small random variable and the small weight by the large random variable. You could see this if these are all the not random variables, and in fact deterministic numbers. But for random variables, this is also the same, which means that. And now we use a property of the hazard rate order, which is that if you have 2 random variables that are ranked in the hazard rate order, then if you apply them to any non-decreasing and convex function, these expectations are going to be ranked as well. Notice that the max function is non-decreasing and convex. So then if you apply this to this larger random variable, results in a larger number than if you apply it to the smaller random variable. So you would want to multiply the larger weight by the smaller random variable. And this would contradict the uniqueness of optimal weight. It's something that I haven't told you, but that's something we established in the paper. So I'll have some extensions to discuss for you. I think each of them are quite interesting. The first one is that we discussed profit maximizing mechanism. We could say, what are Pareto optimal mechanisms? Because what if it is not the seller who's choosing the mechanism? It's somehow some process that specifies the mechanism. All we know is that this mechanism must be Pareto optimal. How do Pareto optimal mechanisms look like? You're going to see that it is in fact a very direct extension of our profit maximizing mechanism. So it's going to look very similar. Then you could ask, what if we had fixed agents were actually paying out of pocket, but in a fixed shares? So we'd have a condo association where I pay 10% of the fees and other people who have larger houses pay a higher percentage of the fees, but these are fixed a priori. You're going to show that this model is going to actually be reduced to our model, and therefore whatever we have set so far applies to this setting as well. Then I'm going to talk about relaxing the veto bargaining assumption. And we're going to see there's going to be some serious conceptual challenges about how we actually think about relaxing the veto bargaining problem. And it's not completely clear how to do that. And then finally, I will argue that all posted pricing mechanisms are suboptimal, and they're not even optimal approximately. So that's the plan that I have. So Pareto optimality. Notice that a given mechanism induces a profile of payoffs for all of our agents. So that's going to be a profile of n+1, one for each agent and one for the seller, right? So you can now think about the space of all possible mechanisms, the space of all possible induced payoffs, and ask, what is the Pareto frontier of that space of all possible payoffs? And what mechanisms obtain a point on this Pareto frontier? A parallel to what we have seen specifies what Pareto optimal mechanisms are. We're still going to have our weights, W star, exactly the way we had before. These are the weights that you put on the virtual values of the agents. But on top of that, we're going to have a profile of weights, lambdas. These are applying to agents' real values, not their virtual values. Because now we may also care about not only the virtual value, because that's the revenue to the seller, but also the true values, because these are the payoffs to the agents. On top of those, we're going to have another weight, which specifies what weight you would want to put on the seller's profit relative to the agent's payoffs. So then part one says, your allocation maximizes the weighted sum of not only virtual values, but also the real values of the agents. So it looks like this. You would put some 1 gamma weight on the seller's payoff. So the seller's payoff is exactly as before. There's W star i's multiplied by the virtual values. Then you would put a weight of gamma on the agent's values. And for each agent, now you're going to have some lambda I that specifies how much relative weight you would put on this agent's value as opposed to the other agent's payoffs. The weights W star, exactly as before, minimize this weighted expected virtual surplus according to this optimal allocation rule that we have. And the transfer rules are defined appropriately. Again, this goes to our whole back discussion about you have to choose them to satisfy the payment identity and then make the IR of one agent bind. The other extension I want to discuss is what if agents do pay out of pockets, but in fixed shares? The example, as I mentioned, is you have a condo association. One agent is responsible for 10% of the fees. The other agent is 20% and so on. But now they're paying out of pocket. This setting can be reduced to our setting. How? Suppose this is the case that agent I pays a fixed fraction of how much the whole group has to pay the seller. So sigma I is how much agent I pays. So these are the fixed shares of the agents. So the agent I's payoff is her value for the product, VIX, minus how much she pays, sigma IM. This is now just a normalization. It's going to take us to our model, which is that let's define theta I to be VI divided by how much I'm on the hook to pay for the product. So now agent I's payoff is just sigma I times theta IX minus M. This sigma I is just this constant multiplier by my payoff, so it doesn't matter. I can just drop sigma I. It doesn't matter, it doesn't affect my behavior. So now it's as if I have value theta I for this product, and the group is paying M, and I'm this is collective money exactly as our setting. So this is just a normalization, takes us to our original setting. So now everything we said applies to this setting as well, namely that the optimal mechanism is a weighted sum of agents' virtual values if their true values were thetas. And even more, we can now compare these weights according to how these sigmas are heterogeneous from each other. In particular, you can say that, suppose that all these true values are IID from each other, but the shares are ranked in a way that sigma I is the smallest share, so this is the agent who has to pay the least, and sigma n is the agent who has to pay the most. Notice that if this is the case, then the distribution of theta i's are going to be identical up to these scalar multipliers. And remember that I had this proposition before that said, what would we do if these are scalar multipliers of each other? We just could rank them like this. So what this says is that the agent who has to pay the least is the agent who is paid least attention to. The agent who has to pay the most is the agent who is paid most attention to. So the person who is on the hook most is the most important agent for this setting.
And with more than two agents, do you still have that result that sort of Wn star is larger than sigma n and so on, if you redefine these as shares? Yeah.
Yes. So even though I showed it only for two agents, that was for any number.
That idea will work. Okay.
Yeah.
In fact, I think this rescaling or normalization is implicit a little bit in your setting, because otherwise the sum of payments from the agents would not be equal. It's the payment of the seller, right? So it's a bit easier to think about the model if there is 1 over n in front of the payment of each agent.
I think it is important, like both settings could be thought of, but I think one of the novelties of this paper is to think about a common transfer setting as well, which is the group is paying M. All your preference is defined is over this outcome, which is the space of allocations and M. So it doesn't matter that you don't really necessarily need that the payments cancel, because we would need that if you're summing up the utilities. You're never summing up any utilities in this setting. So the fact that these transfers don't cancel is not an issue.
Right, but I guess in this logic there is this implicit this kind of normalization might work. There is this implicit quasi-linearity in these transfers and higher scale.
Yeah, absolutely. Yeah. All right, so let me talk about relaxing the veto bargaining assumption, which is that each agent has the power to veto this mechanism, which, as I said, is a very strong and important assumption. You could ask, what would happen if the mechanism doesn't need to be approved by all agents? Maybe it only needs to be approved by some k less than n agents. And basically what I want to point out here is that there's some serious conceptual difficulties with asking this question, so it's not even clear how to ask this. So let me suggest some possible ways. One is that there's a fixed set of agents. So k agents, agents 1, 3, and 7, are the ones who should approve this mechanism, otherwise nobody interacts with it. Well, in this case, we can just design the mechanism for these k agents. These are the agents whose IR constraint matters. So then the problem is exactly the way as we have solved. A perhaps more interesting way to think about it is, well, what if this coalition that needs to approve the mechanism could be flexible? As in, what if the seller announces the mechanism, the agents vote, each of them votes yes or no, do they want to interact with this mechanism or not? And if at least k agents approve participation in this mechanism, then everybody is going to participate in this mechanism. So each agent has a vote for rejecting or accepting this mechanism. In this setting, the seller's optimal profit is unbounded. There's silly things that the seller can do that is not completely satisfying, but technically is valid in this setting. For example, you can say, my mechanism is, I don't give you the product, and you as a group pay me $1 million. There is an equilibrium in which everybody votes yes. Because if everybody else is voting yes, given that only an approval of k less than n agents is required, no agent is pivotal. So then for you also voting yes, it would be a best response. So everybody voting yes is an equilibrium in which the seller extracts an unbounded amount of money. You could say, well, voting yes is dominated. Could it be that the seller extracts unbounded money even in undominated equilibria? The answer is that yes. You could tweak this mechanism and say, in fact, if you all vote yes, I'm going to charge you M. But if one of you or more than one of you vote no, I'm going to punish you. You're going to pay me M plus 1. So now again, if everybody else is voting yes, now you're strictly preferred to vote yes, because by voting yes, you as a group pay M. But if you are the only person who pays no, the group pays M plus 1. So this is then voting yes is undominated. You could fairly point out that this mechanism, even though it has an equilibrium in which the profit is unbounded, there are other equilibria in which all agents vote no. So what about worst case equilibria? But that is would be moving beyond the standard toolkit of the mechanism design that we have, that we're applying in this paper. It would be definitely interesting, but it's beyond the scope of this paper. Yeah.
Sorry, Nima, I was going to bring this up later, but I just got distracted for 2 seconds. So I'm wondering, because I was thinking about this, what if a group could sort of try to figure out what's the best way to protect against the seller? This is what you just mentioned, that you said you didn't look at this. Is that right?
I'm not sure what you mean by protect against, but are you asking?
Well, commit ex ante before these are realized, to even more general than majority, to a sort of a, you need to deal, reduce information available to the seller, reduce access to people, all sorts of things. Perhaps impose that not any majority, but the majority needs to include a certain number of individuals and so on and so forth. So everything else that one can do. You guys have thought about this or not? Or you're saying we're going to do this another time? That's what I missed.
This issue of what would happen if the mechanism. So basically the question is, what is the class of all the games we allow? Before I had allowed all the games in which the approval of all agents were required, and I showed you what happens. Now you're asking, what if you think of all the games in which there's some kind of, not everybody's approval is required? My short answer is that I don't know how to ask this question in a right way. So we haven't thought about it. We don't have an answer for that. And these are the difficulties that I am pointing out here. I hope that answers your question.
Yeah, it does. Thank you.
Okay, thanks. So to avoid this issue, you could say, what if the agent, the mechanism designer doesn't see who voted what? All the mechanism designer sees is that agents vote to a mediator, and then the mediator announces to the mechanism designer if the mechanism is approved or not. So then you cannot say, I punish you if more of you vote no. The conceptual challenge here is that now once the agents see that the mechanism is approved, each agent has to update what they think about other agents' values, because now across equilibria, this might tell you something about the values of other agents. So you're no longer facing a setting where agents have just common beliefs about each other's values, and that's again going to make things much more difficult, and we don't know how to apply the standard tools to that. So the final actual result that I want to show you that we have is that posting pricing mechanisms are not even approximately optimal. To state this formally, what I will do is to say, let's define first of all, it's not clear what a posted pricing mechanism is. But let's define it as generally as you could imagine in a way that still captures somehow posted pricing. And I will show you, even with this very general definition, no mechanism in this class is even close approximately to the optimal mechanisms. So how can you define posted pricing in a way that it maintains the spirit of posted pricing? You could say the mechanism is such that there is some number P, such that the payment is P times X, meaning if the product is sold, the group pays P, otherwise the group pays nothing. So this is saying, let's not impose any constraint on what X is. Let's just say that whenever the product is sold, the group pays P. So this would be a price tag that is on the product, but it could be, the allocation could be complicated. It could be one person agrees, it could be everybody has to agree, it could be anything. And so this is a very general definition of what posted pricing mechanisms are. And we construct an example where as the number of agents goes to infinity, the optimal revenue among all posted pricing mechanisms relative to the optimal revenue goes to 0. So posted pricing mechanisms are not even approximately optimal. Let me just discuss some related literature, and then I'm happy to conclude and then take some questions. Our setting is in the middle ground between two very large literatures that study public good. One is where they allow for arbitrary transfers between the agents, and one is where there is no transfers allowed whatsoever. So mechanisms for public goods, for example, one notable paper is Guth and Helweg, which basically study our setting with individual transfers. So any transfer between individuals are allowed. On the other extreme is there's absolutely no transfer. So this would be literature on voting mechanisms with no transfers. Ours is somewhere in the middle. Public money exists, but it's public. So it cannot have arbitrary transfers. Our work relates to the reduced form implementation literature, like Border and Matthews, in the sense that we had this implementation result of the interim transfer rules. And we, as far as we know, that was a novel result that said all that public transfer requires from you is that the expected transfers agree with each other, and we have an implementation of such transfers. BIC equivalence fails in our setting in the sense that the optimal mechanism that I showed you, it is Bayesian incentive compatible, but it is not dominant strategy incentive compatible. In fact, we show that in almost all interesting cases, except for special cases, dominant strategy incentive compatible mechanisms are not optimal. So this stands in contrast with a large literature that basically shows that in settings with individual transfers, there is an equivalence between BIC and DIC mechanisms, that you can convert any Bayesian incentive compatible mechanism to a dominant strategy incentive compatible mechanism. So let me just conclude.
But they themselves point out that individual rationality can throw a spanner into the works, and you have more complicated individual rationality.
Fair, yeah. So we study a setting with a single seller and a single product and a single buyer. So it's technically a single entity that is buying this product. But of course, this buyer is a group of agents who have, there are multiple agents who are making decisions within this group. And we see that even though there is this single buyer, the posted pricing mechanism is not optimal. So we have to pay attention to the internal organization of this group when we are thinking about designing optimal mechanisms. You need to pay more attention to weaker agents whose IR constraints bind more seriously. One more thing that I wanted to point out is that it could be interesting to study our model with correlation, because in our setting, we could not apply a Kramer-MacLane kind of trick where you design a bet for each agent individually, because exactly you cannot design individual transfers. So it could be possible that even the correlated problem can be answered meaningfully in a way that you don't get a full surplus extraction result. And that's all I have. Thank you.
Thank you very much, Nima. Excellent talk. So you're right on time. This is impressive. So we are moving now to a Q&A sessions, 15 minutes. As usually, we are going to start with our panelists, whether they have any last comments or final questions. but we will also include obviously the audience. Any, Alex, Mallesh, would you want to say or ask anything?
I have a question. It's actually related to this slide. As Nima mentioned that indeed, I think the question of correlated values is maybe non-trivial and natural in your setting in particular, because in your examples, in some sense, you have this external seller that approaches some group of agents that operate within one company. So in some sense, it is natural that they might have some correlated values, but in fact, I also have a feeling that it is natural that the communication between the seller and these buyers might be structured in a bit different way than the mechanism that you have. In particular, I have a feeling that your construction relies a lot on this possibility of private communication between the seller and each buyer. For example, if you think about your leading example, right? If you are remember CEO probably with the very low value, in some sense. Whenever you report your value, you actually do not know what CTO reported, right? So you do not know, in some sense, whether the trade will actually happen or not. And I find it a little bit strong because, in some sense, more natural for me would be that in some sense they communicate between each other, maybe through the channel that's designed by the seller, but then they see the outcome of the communication, of the joint communication, and this is when they can veto. Because in some sense, in your mechanism, it can be very well be that you as a CEO, you have very low, but then turns out the CTO had high and he wants to buy, and you see this order going to the seller, and then you can veto. I have a feeling that this is not allowed in your mechanism, and I was thinking whether you could think about it, and in fact, whether they could restore, in some sense, this posting price optimality. Because I thought an alternative setting could be that you as a seller, you, for example, offer a mechanism of communication between all these buyers and yourself, but then at the end, each buyer can veto this public message that goes to the seller. And whether in that setting, posting mechanism could be optimal or not. So that is my question.
Yeah, no, that's, I think, fair. And Alex, I'm sorry, Elliot and Aditya, feel free to express your opinion as well. I think that's an important question, but to think about what does this mechanism design mean if there is some kind of communication between the agents prior to the design of this mechanism. So in some sense, it kind of takes us outside of this scope of mechanism design where all possible games are possible. Now you have to think about games that have a maybe pre-communication step. Yeah, I think once you do have such pre-communication step, then possibly things are going to be quite different from each other, because we are assuming that you have to vote yes or no, knowing your own value without knowing anything else about other agents, and then whatever the seller designs in terms of communication is designed by the seller. Elliot and Aditya, is that?
I mean, yeah, so that's what I would take as the most literal interpretation of the model. But of course, we're also just we think the broad setting is of clear interest, and we thought this seemed like as a first step to understanding the environment. This seemed like a natural one.
Can I ask kind of follow-up questions also to Francesco's? If you tried to take the group and just for a second, just for comparison, not taken seriously, treat it as a unitary player that has their own objective, which is, I don't know, some sort of internal Pareto efficiency or welfare thing, and treat it unitary. Obviously, it would take us slightly further away from Meyerson's because we would have a player with the multiple values, but would that be a useful benchmark if that could be solved?
I agree. I think that would be an interesting benchmark, but if that benchmark is this unitary player is somehow an expected utility maximizer with some value V, then that would take us back to posted pricing. So,
but in the context of the model, we would imagine, that this group actually has a way to coordinate among themselves. In terms of kind of numerical result, whether that would, in what direction it would take us, and what would those weights, would there be a corresponding magnitude or some interesting parameter or?
That's
anyway. Sorry, Mallesh, do you have any other questions?
I wanted to go back a little. I mean, I guess I missed or didn't understand the section on sort of n out of k, or k out of n people. So I didn't understand what that construction was trying to do. And that's sort of on me, but I don't want to hog the discussion, so maybe I can catch them later. I mean, I think it's a fascinating question. It seemed like your construction was somehow forcing the agents into this mechanism by constructing, but then I was doing a sidebar and I should apologize for that. It seemed like it was forcing them into a mechanism that was ex ante, that in equilibrium, they'd all agree to be in the mechanism, but they're all just being screwed by it.
absolutely.
And it didn't seem like it captured the spirit of what it would mean for getting K out of N to agree to a price. I don't know if I have a better phrased version than that. But, I mean, I feel like that's an important question, right? Like when we think about doing mechanism design, where there is a group of agents, like if I'm trying to do tax reform, I want 60% of the people to agree to the tax reform before I can pass the tax reform. But you're just telling me there's an undominated equilibrium where everyone, Elliot's disagreeing. So I clearly have missed the nuance.
No, I think that was exactly the point. In fact, the point was to say that how do you want to model this fact of K out of N agents agreeing? If all you want to do is to say you want to have equilibria in which when K out of N agents vote yes, the mechanism is interacted with, then we have this silly equilibria in which everybody does vote yes, even though everybody is being screwed. So then how do you want to think about these N agents or K agents agreeing to this mechanism and have equilibria that are meaningfully representing this fact that you wouldn't vote yes even if everybody's being screwed?
I don't have a better solution. I didn't misunderstand it. So
No. We didn't have a solution either. That was just pointing out this exact same thing that you're saying.
Okay.
Yeah.
And how?
If I have a question, if I may. So, I mean, this is really amazing. I mean, how tractable the setting that you are providing today is, and I guess that's the reason why you can do so many extensions. There's one though that I wonder whether you can explore, which seems interesting to me, because the way I think about this is that we have studied the problem in which the decision to be taken is private and the money is private. That's basically Meyerson, 1981 auction design. We have studied the problem of optimal public good procurement, which is basically when the decision is public, but the money is private. Now you are proposing the case in which both the decision and the money are public, but I wonder what happens when the decision is private, but the money is public. Now, for instance, think of the European Union. They have to build a new lab. Is it going to be in France, in Germany? Is it going to be in Spain? You see? So, there are reasonable examples. And to some extent, I kind of try to kind of conjecture that everything you have said here should apply to this case as well. Because at the end of the day, the model is simply a model in which the asymmetric information is about the marginal rate of substitution between the two decisions. So it seems that everything should go through naturally.
I think I agree. I think, that implementation lemma that we discussed, it didn't really care what the space of feasible allocation rules X's are. It talks about you only need interim monotonicity to implement a given allocation rule. So then you can write the min-max problem. I want to say, again, Aditya and Elliot, feel free to disagree. I agree with you. I think I agree with you that even with a private good, public money, many of the things we said would be the same.
So I would say the starting point of the analysis and the reduction to the standard framework. So all the stuff that makes life tractable for us would go through perfectly. So we'd still have that all that matters is that the mean transfer is the same when you're just thinking about BIC. And we would still have that that we can use, write things in terms of virtual values and phrase everything as an optimization just over allocation rules, subject to some interim monotonicity constraint. All that would go through. The things that are more like the weighted voting rule structure that we had exactly, I wouldn't expect that we would have something like that. I kind of expect that like similar duality tricks would work to get other things that have weighted votes in them or something. But then, and also the analysis about, weaker agents being weighted more is specific to like, what is the nature of the allocation?
Just the final thought. Maybe I'm getting confused at this point, but just trying to put together everything that you have said, probably I could rephrase my question the following way. Okay, you study public, okay, and it's very different from either private when it comes to private money and public decision, or private, of course. Okay, so now the question is, when you have public money but private decision, is it going to be closer to your setting, or is it going to be closer to the standard public good problem?
Wait, sorry, you're saying when money is public but the good is private, like
exactly, like when
you have XI, right? You mean XI for each eye, XI for each eye.
Exactly.
It's going
it's basically where to allocate the new lab, no? In Germany, in Spain, in the UK, but we are using public money for this.
It's going to look like I feel like I can pretty confidently say it's going to look like a combination of the analysis you've seen here and the analysis that's in the Meyerson problem. Maybe my co-authors will disagree with my very bullish statement.
I don't see how after this max min, how do we proceed when you have XIs? That's my
we're not even at the
no, I'm saying most likely we will get to max min. I don't see what follows.
Yeah.
Have XIs.
I see.
But the main thing we did that opened things up to make it tractable and kind of in particular reduce implementability to the standard case, that would apply readily. And so basically I'm expressing, it's not that I think the substantive economic results will be repeats of what you would see here, but I'm expressing confidence that that would be a tractable problem to study.
Yeah.
Diplomatic as always. Okay, this is 5:15. I have some questions, but let's finish here the official part. So thank you, Nima, for the excellent presentation, co-authors for the participation and